Oh, actually, we'll review. This is a meter stick. Class, how long is a meter stick?
1 meter.
1 meter. For some reason, people forget that a meter stick is 1 meter long. Please do not forget that a meter stick has a length of 1 meter. We call it a meter stick so often, you guys forget what that actually means. Okay, so what I'm going to do is I'm going to take the meter stick, I'm going to hold it right here, I'm going to take a ½ kilogram mass, I'm going to place it at the 70 centimeter mark, and I'm going to hold it like this. This is the situation. What we're going to do is we're going to go through and analyze the forces that are acting in this particular situation. And I cannot draw on the board and do this at the same time. So you're going to have to take a mental picture. And then I'm going to go draw on the board. So we are taking a ½ kilogram mass and placing it on the meter stick. Okay, so the mass of the mass is 0.50 kilograms. The mass of the stick we need is 88.6 grams, or 0.0886 kilograms. We need a picture, so let's draw our picture. We have the meter stick, looks like this. We have the desk, which is right here, which I'll just show like this. We have our desk holding up the meter stick on one end, and we have the mass, which was located at the 70 centimeter mark, or 0.30 meters from the end, and my hand was on this end. What we're going to do now is we're going to go through and draw the free body diagram, bless you, of all the forces acting on the meter stick. All the forces acting on the meter stick. Christina, give me a force acting on the meter stick, please. From what?
On the meter stick?
Okay, force of gravity of the meter stick?
No, force of gravity.
Yes. acting on what?
Onto the meter stick.
From what? You'll understand why I confused it.
Oh, the mass?
Right, so what are we talking about here?
Force of the mass.
Okay, there's a force of gravity from the mass acting on the meter stick. And I think you'll understand the confusion in just a moment. Okay? Heather.
There's a force of gravity of the meter stick on the meter stick.
Where does that force of gravity act on the meter stick?
In the middle.
In the middle, what is called the center of mass. We're going to assume it's a uniform meter stick, therefore it will be directly in the middle. So there's a force of gravity acting on the meter stick itself. So you can see the confusion. You have to identify there are two different forces of gravity, one from the mass, one from the stick. Both these forces are acting on the meter stick. More forces. Hannah. Okay, we need more forces. Low?
The force applied from me.
Where?
On the left side of the meter stick.
On the left side of the meter stick, and I was applying a force upward, so the force applied by me on the far left. Lily?
Force up, or the normal, force normal
On the table. Force normal on the table. From the desk on the meter stick, we have a force normal.
Is there also force of static friction between the table and the meter stick?
Technically, if I were to apply a force straight upward, there would be no force of static friction because there would be no other forces in the x direction. So it's an ideal case. I'm very good at only applying force directly upward. Andrew.
Would you say force normal's in the middle of the meter stick because like your hand is also applying force normal?
We're going to call mine a force applied. You could call it a force normal if you wanted to, but that would be force normal 1 and that would be force normal 2. It's easier to separate the two here. Is there a force normal acting up on the mass, class? Yes. Why is it not going to be in our free body diagram? Heather.
It's
Oh, you need to think carefully about what we're drawing the forces on. What I said specifically is we're drawing the forces acting on the meter stick, right? Is there the force normal that acts on that mass doesn't act on the meter stick, but that mass pushes down on the meter stick with its force of gravity, right? So So because we're only drawing the forces acting on the meter stick, this is a complete free body diagram with no force normal on the mass. Now, notice that this free body diagram is different than any other free body diagram we've drawn so far in this class. How is it different? We've done ones where all the forces were in the y direction, so it's not that they're all in the y direction. Correct.
Forces are all from the center of mass.
Every one we've done before has had all the forces coming from the center of mass. Now we have to be concerned with where they are, where they're acting, because we have torque. So because we've started to work with torque, we need to be concerned with exactly where those forces are applied. So you need to be careful with that. Now, what we're going to do here is we're going to solve for the force applied, and we're going to solve for the force normal. That's what we're going to do in this situation. Now, looking at this, what type of equilibrium is this object in? It is in rotational equilibrium. I agree with that. What else, Pooja? It is also in translational equilibrium. Therefore, class, it is in static equilibrium. Great. So because it's in static equilibrium, we can sum the forces, and the force is going to be equal to 0, sum the torques is going to be equal to 0. We can pick any axis of rotation. Now, let's start out by looking at what happens if we sum the forces in the y direction. When we sum the forces in the y direction, we get the force applied, which is positive. We get the force of gravity of the mass, which is down and it's negative, the force of gravity of the stick, which is down and it's negative, and the force normal, which is up and positive. That's equal to mass times acceleration in the y direction. The acceleration in the y direction is equal to 0. Now, why, at this point, is this actually not all that useful? At this point, it doesn't help us too much. Christine, why does this not help us very much?
Because everything is equal to 0.
Just because everything's equal to 0 doesn't mean it's not helpful. That's actually, when things are equal to 0 is actually very helpful. Why is this not overly helpful? Rick?
There's two unknowns.
There are two unknowns. At this point, this is one equation with two unknowns, the force applied and the force normal. So we can't actually solve this equation. So rather than looking at the fact that it's in translational equilibrium, we're going to use the fact that it's in rotational equilibrium, and we're going to sum the torques. We can pick an axis of rotation. This time, I will pick an axis of rotation. So we will start by picking the force applied as our axis of rotation. So, summing the torques with our axis of rotation at the force applied, that's going to be equal to, I'm just going to list all the torques that could possibly be there. We have the torque due to the force applied. We have the torque due to the force of gravity of the mass, the torque due to the force of gravity of the stick, and the torque due to the force normal. All of those are going to add up to 0. What you need to do now is to go through and figure out whether they are positive or negative using your right hand. So take a moment and figure out whether they are positive or negative. Now, before I go through which ones are positive, which ones are negative, I want to point out that when I introduce torque, for some reason, and the right-hand rule, for some reason, people start to get really confused. And they do things like, I ask them, what's the direction of the force of gravity? And they pull out their right hand and they limber up. But you don't need your right hand to figure out what the direction of a force is, right? Right? It's still up, it's down, it's left, it's right. It's in the board, it's out of the board. It's just the direction of a force. You only need to use the right-hand rule for the direction of a torque. And it's important to keep the two distinction between the two. So Lily, walk me through the different directions of the torques due to the various items.
Well, put the axis of rotation somewhere down on one of them. between like the force of gravity of the stick and the force.
I picked an axis of rotation. It's at the force applied.
Oh, I'm just kidding.
That's okay. And now I understand what you're doing. I've already picked our axis of rotation. It's right there.
Oh, okay. Well then the force applied, that's 0.
Okay, stop for a second. And this is very common for people to say. And you need to listen to what she said, and I'm not picking on you. This happens almost every time. Say it again. It's not right.
The force applied is 0.
One more time.
Oh,
The force applied is 0. Is that true, class? No. What is true? The torque due to the force applied is equal to 0. So you have to be very careful. Again, Lily, why is the torque due to the force applied equal to 0?
Because the angle, there's no angle.
Well, technically there's no angle because Carlos, help her out.
There's no lever.
Because there's no lever arm. So because the lever arm for the force applied is equal to 0, the torque due to the force applied is equal to 0. Okay. And you'll notice that's actually why I picked the force applied as our axis of rotation, because then the torque due to the force applied goes to 0, and the force applied will not be in this equation anymore, and we will only have one unknown, as opposed to the equation we had before. I only asked the torque due to the force of gravity in the max direction.
Negative.
How do we get that?
Oh, put your hand in the system of right under the rotation, then you put your fingers the lever arm.
Point your fingers along the lever arm.
And curl your fingers to the direction of force.
And therefore, we found points into the board, so we get negative for the force of gravity, torque due to the force of gravity of mass, negative for the torque due to the force of gravity of the stick, and positive for the torque due to the force normal. Great. So negative, bless you, negative, and positive. So now I'm just going to plug in force times lever arm times the sine of the angle for each one of these. So we get negative force of gravity of the mass times the lever arm for the mass times the sine theta for the mass minus the force of gravity of the stick times the lever arm of the stick times the sine theta for the stick plus the force normal times the lever arm for the force normal times the sine theta for the force normal. Again, all I'm doing there is plugging in force, lever arm, sine theta for each of these. Class, what's the equation for the force of gravity? Oh boy. Class, what's the equation for the force of gravity?
Mass times acceleration due to gravity.
So I'm just going to plug in mass times the acceleration due to gravity for each one of these two forces of gravity. So we get negative mass of the mass times the acceleration due to gravity times the lever arm of the mass times the sine of theta for the mass minus the mass of the stick times the acceleration due to gravity times the lever arm of the stick times the sine of the angle for the stick plus the force normal times the lever arm for the force normal times the sine of the angle for the force normal. From left to right, please give me all of the numbers. Dan Herbert. Negative mass of the mass.
That is 0.5 kilograms.
Good. The acceleration due to gravity here on planet Earth.
9.8.
Positive or negative?
Positive.
Are you positive?
I'm positive.
Why are you positive?
Because I'm a little
Thank you, Dan Herbert. Absolutely. That's wonderful. Because she is always positive. Great. Lever arm for the mass.
90 degrees, sine of 90.
I agree with the sine of 90 degrees, but I need the lever arm first.
Oh, that is 0.3.
0.3. Let's look. With the axis of rotation is here, the force of gravity of the mass is here, so I agree 0.3. Keep going. Mass of the stick.
0.0886 kilograms times positive 9.8.
Times the lever arm for the stick.
0.5 meters, that's halfway.
Halfway, if you'll notice the distance from the axis of rotation to where the force of gravity of the stick is half of the meter stick times the sine of
90 again.
90 plus the force normal, which we're solving for. The lever arm for the force normal is
1 meter.
1 meter. Notice it's the entire length of the 1 meter long meter stick. And the sine of?
The sine of 90.
Again, the sine of 90. So it all equals 0. So we have one equation, one unknown. Class, please tell me what is the value for the force normal. Last one.
1.90414.
1.90414 independent confirmation, 1.90, etc. Good. Okay. So with sig figs, 1.9 newtons. We are halfway there. We have figured out the force normal. We are going to figure out next the force applied. There are two ways to do this. One is the easy way, one is the difficult way. We're going to talk about the easy way, then we're going to do it the difficult way. Who can tell me? Who can tell me what the easy way would be? Look.
Putting the axis of rotation where the force normal was applied.
Notice, because it's in static equilibrium, we can pick any axis of rotation, so we can move the axis of rotation. This is actually the difficult thing. The easy way is much easier. It's also in translational equilibrium, so we could completely ignore torque at this point because we figured out the force normal. We now have one equation with just one unknown. The reason we're going to do it the more difficult way is because we need to review some of the torques, some of the forces we've done often enough that we don't really need to review them. But I would suggest that when you do solve a problem, for example, on a worksheet, I won't say quiz, but I'll say worksheet, then I would suggest doing it the easy way, because there's no reason to do it the hard way, except when you're learning how to do it, like right now. So again, we can pick any axis of rotation. Low, you suggested what?
Putting the axis of rotation where the force normal was acting.
Okay, so we can put it wherever we want. And we're going to, according to Low, we're going to put the axis of rotation at the force normal. Okay, so this is axis of rotation number 1. This is axis of rotation number 2. Again, we have all of our various torques: torque due to the force applied, torque due to the force of gravity of the mass, torque due to the force of gravity of the stick, and torque due to the force normal. All those add up to 0. Please, Hannah, give me all the positives and negatives.
The torque due to the force normal would be 0.
Because?
Because the handle is, there's no lever arm.
Because there's no lever arm. Good.
And then the torque due to the force of acceleration would be,
Force applied.
or force applied would be into the force, that would be negative.
Okay, we start at the axis of rotation, we point our fingers along the lever arm, we curl our fingers in the direction of the force, I agree, into the board, so the torque due to the force applied is negative.
And then the other two would be out of the board, so it'd be positive.
I agree, we can go through the same thing, we'll get positive for each of those. So then, again, we substitute in the equation force, lever arm, sine theta for each one, negative force applied, lever arm for the force applied, sine angle of the force applied, plus the force of gravity of the mass, lever arm for the mass, times the sine theta of the mass, plus the force of gravity of the stick, times the lever arm of the stick, times the sine theta of the stick, equals 0. Therefore, again, we can just plug in mass times the acceleration due to gravity for the force of gravity, negative force applied, lever arm for the force applied, sine of the angle for the force applied, plus the mass, the acceleration due to gravity, times the lever arm of the mass, times the sine theta of the mass, plus the mass of the stick, times the acceleration due to gravity, times the lever arm of the stick, times the sine theta of the stick. Again, simply substituting in mass times the acceleration due to gravity for the force of gravity, and force, lever arm, sine theta. From left to right. Jessica, please give me all the numbers.
Very force applied, just leave it like that.
That's what we're solving for. Lever arm for the force applied.
The lever arm is 1 negative.
Great. Sine of,
Sine of 90 degrees.
plus the mass of the mass,
0.5.
times the acceleration due to gravity.
9.8.
Good. The lever arm of the mass.
It's 0.78.
Notice that that is going to be the distance from the axis of rotation to where the object is, so 1 minus 0.34. Good. Sine of,
Sine of 90 degrees.
plus the mass of the stick.
0.0886.
Acceleration due to gravity here on planet Earth.
9.8.
And the lever arm for the stick.
0.5.
Half of the meter stick and the sine of,
90 degrees.
and all of that adds up to 0. At this point, we have one unknown, one equation, class, using the force applied. 3.86414, independent confirmation 3.86, yes? Good. So 3.9 newtons. To reiterate, I do suggest doing it the easier way. You're going to make fewer mistakes. That's a suggestion.